to the next tutorial, number 1.2. And again, we will take this a little slower than the other tutorials, because there's a lot of stuff that, if you haven't used NGSolve before, there's a lot of stuff here that is very useful for dealing with the software. So the coefficient function is central in NGSolve. They are representations of functions on a domain, or a domain after meshing. The mesh object is what you saw in the previous tutorial. Once you have a mesh object, you can define coefficient functions using the coordinates x, y, z, and so forth. And the coordinates themselves are coefficient functions. So we will see a lot of things related to the coefficient function in this tutorial, like defining, visualizing, evaluating, and then we will look at the expression tree of a coefficient function to know how it's internally stored, and that then allows us to do things like optimization of evaluations of the coefficient functions, or at least understand what the commands to optimize do. And we can integrate, differentiate, we can include parameters that change later in some stage in the computation, interpolate, etc., etc. So let's begin. Let's begin by creating some mesh. Here is the unit square mesh, a mesh of a unit square. And here's a function. It's the definition is transparent. It's x times 1 minus x. This object x was imported when you from the first line. When you say from NGSolve import star, it imports a lot of stuff, and x and y are imported that way. And you can wonder, what is this x and what is its data type? And you see that they're all coefficient functions. So x is a representation of the first coordinate as this object coefficient functions. So certainly, if we want to build functions out of x, we need to understand what this coefficient function is. So here are things you can do with once you declare a function. You can ask it to be visualized using the draw command. You can ask it to be evaluated, provided you have a mesh. So the mesh knows how to evaluate a coefficient function. So you give you want to evaluate this function at the point x equals 0.2, y equals 0.2. You give that x, y coordinates to the mesh. It then returns an object called a mapped integration point object, which can be passed into a coefficient function, and it'll evaluate the coefficient function at that point and give you a number. Okay, this is a usual mistake. Sometimes I do this too. Instead of doing this mesh, you put in the xy coordinates right there, and nothing happens. Okay, so you have to first use the mesh to get a mapped integration point, and then pass that into the coefficient function. Okay, and you can not only evaluate the function at a single point, you can evaluate it at a set of points. So here's a set of points. You make a list comprehension of a number of points, say 11 points here, and then pass it to this function, and you get a list of values. And for example, you can plot this set of values or print out this set of values. Here we're printing out the value of this function at a number of points. Okay, now if you have 100,000 points that you want to evaluate, if you do this list comprehension, it's going to be slow. So you want a vectorized version, and here's a vectorized version. The vectorized version using NumPy creates the array in one shot, all the points that you want, all the x coordinates and the y coordinates in one shot, and then mesh xy then gives you a whole. We're not printing out this list, and that can be passed to the function, and it'll give you the whole list efficiently as a NumPy array. And you can plot this set of values of a function. Remember, the function that we're dealing with, my func, is x times 1 minus x. If you plot it, it's going to look like this. Okay, now for the representation of coefficient functions internally, if you print a coefficient function, you will see a printout of an expression tree. So let's look at this here. Here's x times 1 minus x. This is being parsed as as a tree. At the top of the tree is the star operation. That's this operation. And the star operation has two leaves. One evaluates x and the other evaluates 1 minus x. So the evaluation of x is right here. The evaluation of 1 minus x is another tree rooted at minus with 1 and x. So that's 1 minus x. And so you see the tree structure. Now you give it a complicated expression, I will not be able to parse the tree, but you can sort of see how this works. So when we say evaluate a coefficient function, it's traversing the tree and evaluating every node of the tree. Okay, and we'll come back to this tree business in a second. But let's see other things that are useful things for a finite element person. Integrate a function. Okay, here's how we integrate. And when you say from NGSolve import, it imports this integrate thing, and you can integrate a function over a mesh, and you can specify the order of integration, or the order of quadrature you want to use. Okay. You can differentiate. Differentiation is done via automatic differentiation. Automatic differentiation is a symbolic process. So let's differentiate the function x times 1 minus x, and the result of the differentiation, if you look at it, it does not look quadratic, it looks linear, so probably did the right thing. And we can actually see what's going on in the implementation if you print out the tree of the differentiated function. So this is what is actually implemented. So the product rule is implemented, and so when you have an expression like this, which because it's a tree containing the star, the differentiation process, the product rule is being implemented, and if you look at the tree carefully, then you'll see that the elements of the product rule here. You see this expression, there's a plus here, so the tree begins with a plus, and these two are the leaves of the tree, and the first leaf here has dx over dx, which is 1, and 1 minus x, and you should be able to see this. I think you see it here. 1 and 1 minus x. Okay, so if you look at it slowly, you'll see both parts of the. This thing is supposed to give you a minus 1 times x, and that's you see scaling by minus 1 and x. Okay, so that's you get an idea of what is being done in the automatic differentiation procedure. You can introduce parameters into coefficient functions. So y is a coefficient function, sine y is a coefficient function, sine of ky is also a coefficient function. The only difference here is that k is declared to be a parameter, which means that you can use this coefficient function with one parameter, and later on you can change the value of the parameter, and it's it knows how to change the evaluation process. Okay, here is sine k times y, more or less looks like a sine. And you can later set k, the value of k to 10, and then you see that also looks like a sine of a higher frequency. And if you look at the expression tree of f, you'll see the parameter that we call k appearing as this thing. So the parameter is a node in the tree, and you can differentiate with respect to nodes in the tree. So therefore you can do f, you can differentiate f with respect to either y or with respect to k, and you can verify that. While if you're an expert in reading trees, you can verify this. It's going to take me a while to get into what this tree is, but alternately you can see if you get the right answer by doing tricks like this. Here's the derivative, and we know how to differentiate, so we make sure that it gave you the right answer by taking the difference and verifying the difference is 0. Okay. The other important thing to do is to interpolate a function into a finite element space. Okay, so a coefficient function, my func, is not the same as a grid function. The grid function is an object which has memory and it represents a function in a finite element space, but you can interpolate a coefficient function into a grid function, and that is done using this operation called set. Okay. Set is synonymous with interpolate. The set actually what it does is a particular type of interpolation that first zeroes the grid function, then projects it element by element in the L2 norm, and then you get a piecewise polynomial that's discontinuous on the mesh, and then you average the degrees of freedom to bring it back into the finite element space you're doing the interpolation. Okay. Fancier ways to do interpolation, I think Joachim will probably talk about it in chapter 2. Okay, so vector valued coefficient functions. So far we've seen scalar valued functions. A vector valued coefficient function, you just have to give a tuple as an argument to coefficient function, a tuple with x and y coordinates or x, y, and z coordinates. Okay, so here's a vector field. And if you're already getting tired of writing coefficient function, then you may write CF. Okay, that's and you can picture the vector function, and in order to picture the vector function, there are arrows. These arrows came up in whetting the appetite on more complicated domains, but you see the arrows are colored, and they're colored according to the magnitude of the vector, and the arrows show the direction of the vector. Okay, here's another example. You can take a scalar function and then take its gradient, and you get a vector function, and you can ask, how does the gradient of a vector function looks like? So a gradient of a Lagrange function is a piecewise constant vector field. So you see that the magnitude of the vector is a piecewise constant function, and I have put a lot of arrows here by prescribing that it should be plotted on a grid of 30 by 30, but I can't see it here. Okay, I think you can see it there. Okay. Yeah. Oh, okay. So just to point out, you can this vectors equals true argument will plot the vectors, and you can tweak it and provide further options in this dictionary, asking you to plot and finding grids and so forth. Okay, now we come to evaluation of coefficient functions, or making the evaluations faster. You can make the evaluations faster by compiling the tree. Okay. Here's how you compile the tree. There's a compile method. But to understand what is happening behind the scenes, we have to look at the difference in the internal structure of the tree-based form, which is the structure we saw before, and the compiled form. The compiled form does not look like a tree. It's a sequence of steps. So what happened is the tree traversal has been transformed into a sequence of linearly ordered steps. And if you want to read this sequence of linearly ordered steps, for example, step number 2 is a binary operation. The operation is minus, and the operation is being conducted on 2 inputs, 1 and 0, but it's not 1 minus 0. It should be interpreted as output of step 1 minus output of step 0. And similarly here, star, it's output of step 0, star, output of step 2. Okay, so the tree has been converted into a linearly ordered sequence of steps, and that's usually faster to evaluate. It's particularly fast to evaluate if the tree has a lot of repeated nodes. So here's an example, cooked up example of an expression with a lot of repetitions, and you'll see the difference in the evaluation times. Instead of evaluation time is very small, so an integrate requires the function to be evaluated at all the integration points, so we are using integrate to measure the time. So that takes, what, 486 microseconds, and if you look at the compiled form, hopefully it'll take less, about 10 times faster. And if you're working with the NGSolve that's built from source instead of a binary install, then you have a compiler script that came with your build. So in that case, the following line will succeed without an error. Otherwise, you might get an error. And that what it's doing is this linearly ordered steps. It's actually sending it to the compiler, to the C++ compiler, with all the options, the same options that were used in compiling NGSolve. And that should give us a little bit more speed. Okay, reduced it by maybe half compared to the so if we didn't do anything, it was 486. If we did the compile, it's 44, and if we did the real compile, then it's 28. So these experiments will give you an idea of how to make the evaluation of an expression tree fast, and you can also look at the trees if you're adventurous. For this expression, the compiled expression has 25 steps, but the tree is really horrible. Okay, well, okay, but I'm not going to parse that. So, okay, there we are.
What's the? Okay. I was just going to ask, what's the order in integrate? What does that mean?
Order is the order of the quadrature. Integration is done by quadrature rule on elements, and you can have high order quadratures. You can omit the argument and it will do some default order. But if you suspect that in some element there's sharp variations, you might want to increase the order.
Nice. Okay.
Questions?
One question: in the tangent, what this loops each? What that means?
Let me go back. What's that? Oh,
10,000 loops each.
To get reliable timings, time it does the same integration 10,000 times, whatever it says. So it did the integrate 1,000 times, and then average the result to get the.
And then the next line is 10,000.
Because it was a shorter time, so it did more of it. Microseconds, yeah. Okay. Any other?
If you create your own coefficient function and you want to give it a derivative,
Yeah.
Sorry,
No.
You want to give it a derivative, you just have to be like, this is the coefficient function derivative.
The derivative, it computed it, but
I mean, if you were to create your own, like, I know there's various ways to set up your own coefficient functions. You just have to know what it is.
Very good point. Yeah. For example, you want to make your own sinus function or some Bessel function and so. You have to provide what is the derivative of this. You have to provide that the derivative of sine is cosine.
As another coefficient function.
Yeah.
Okay. Yeah. Cool. Not numerically, I guess is what I mean.
yeah. An expression involving sine. NGSolve already knows the derivative of sine is cosine, but I don't know if NGSolve knows the derivative of the error function or Bessel function. Yeah.
Luckily, that's the error function derivative, just the.
We know error functions.
Yeah.
If it's a commonly known special function, you probably could do it in some other, like in SymPy or something, and then evaluate that in NGSolve, and you would be able to get a coefficient function that way.
C++ for Bessel function is in NGSolve now.
Oh, is it in NGSolve itself, or is it in
Special coefficient NGSolve?
Not special functions, but special
Yeah.
functions? Yeah, okay.
There is a GitHub page. I think it's called NGS Special Functions, which provides an add-on module for containing Bessel functions.
With Fortran implementation of about 5,000 special functions.
Yeah, this is the same thing.
And this runs also in parallel. When we integrate in parallel, then the call to this function goes also in parallel. Would not work for a sci-fi.
Okay, so we go on to the next tutorial.